So one important thing is we'll have first midterm on Friday. So this is next week. So March 21 this year, Friday. It will be during the class hour and during the class period. So we'll not take the break, of course, but it's going to be close to 2 hours, under 10 minutes, midterm, with 5 questions. We'll have 5 questions, sometimes A and B's, but mostly you should be able to finish it in 2 hours. During the exam, no notes, no calculators, okay? In case you have other exams in your department which allows notes, we do not allow notes or calculators. And actually, since anytime we see you playing with any cell phone or any other thing, we'll be charging you for cheating. It might be best actually we put the cell phones in the front, okay? So either put them in your bag and never touch them, or you put them in the front, okay? But if you ever looked at it, you'll be considered cheating. So I will say no cell phones, because I can actually open a Wikipedia page on my cell phone and learn everything from my cell phone. So I'm sure in the exam you can do that too. So no cell phones. Other things that we need to know. We have 2 classrooms. So for the exam, one of the classrooms is here, but we will have 2 groups. So this is where you need to go. If your last name is less than Karavelioğlu, you go to, you come to this room, okay? So if your last name is bigger than Kartar, okay? So Kartar, Kılıç, Kibar, Koç, Köse, and so on. You go to this original room we have, which is at 05. So it's across the corridor, just a little bit cross. Okay? And they're both big rooms, like this size. And each room will have 17 people, so you'll be sitting very relaxed and very apart from each other. Okay? To get you a little bit more space and make sure no cheating. I mean, you're 3rd or 4th years, you know consequences, so you should not try even cheating. Couple of notes. We have a quiz on Tuesday. On 4th homework assignment, right? Which I gave you last time. Your 3rd homework assignment is graded and came back, so you can pick them up on the 10 minutes break today, okay? So you will be having your first 3 homeworks graded, and the 4th one maybe will be ready, but since it's Tuesday, it probably won't be ready. Other things, on Tuesday we will do problem solving. So we'll not be learning any new material. Everything includes, everything for midterm 1 will be done today. Okay, so whatever you learn today, it's at the end of today's lecture is the coverage. If you look at the syllabus on the internet, you will see that this will mean that this is at the end of week 5, so inclusion exclusion principle. Okay, so we'll be learning inclusion exclusion and stirring numbers, and that's going to be all of it for midterm 1. Now, you will receive a sample exam on the weekend via email. So check your emails. I will also send you a list of suggested problems. I have some old suggested problem lists and exam lists, but each year you did a little bit differently, so I may change some of the questions from the old exams. But essentially, we solved a lot of questions in the class, which are good reflection of what should come in the exam. So another thing, you'll have office hours next week. Now, usual office hour is on Thursday from this time to this time. Okay, and next week you can also come on Tuesday. Tuesday we have class, so if you want to come before the Tuesday class in the morning, I'm available. If you want another office hour, maybe Thursday morning after 11 also possible, but this is I have. Okay, those of you who came late, you can write your names on a piece of paper on the break. You will get a quiz grade, but late, okay? I'll write late. Any questions about midterm or homeworks, quizzes? Okay. If you have any friends who's not here today, you can tell this to them so that they come to the right class, okay? I may write this on the email on the weekend too, but I like to make the announcements in class and make sure everyone comes to the class. So, anything else? Okay, so what you're going to learn today is a new principle. We call it the inclusion-exclusion principle. I guess our identity. Now this will lead what we call a stirring number. Stirring numbers are important for deciding in how many ways you can do certain distributions. So far, you learn a lot of formulas which allows you to count number of ways to distribute. For example, you know how to distribute identical objects to boxes which are distinct. You know how to distribute in an ordered way. You know some formulas, you know the repeated combinations and so on. But there are certain problems that you still can't solve. And for those problems, you will need to know something called stirring numbers. These problems tend to be problems that you're required to map a certain set to another set in a surjective way, in such a way that everything that you send is covered. So because of these things are hard to count without this principle, we first learn this principle. So this is a very simple principle. First, let me show you with two sets. So suppose we have two finite sets, say A and B. Okay? So these are two sets like this. This is A, this is B. And they may have intersections like this. Okay? Now, the number of elements in the union If you know the number of elements in A and number of elements in B, you can say, okay, this is going to be this plus this. But we know that this is not correct, right? Because if you say it's this plus this, what you're doing is you're counting these things too many times. You're counting it first as part of A, then you're counting them as part of B. So to fix this, all you need to do is subtract this overcounting. And you're subtracting exactly elements in the intersection. This is a very simple thing to do. I mean, if you have, you can see that if you have A elements here, B elements here, and say Z number of elements here, just for this part A, this part Z, this part B, you can see that this is A plus Z, this is B plus Z, so Z is overcounted, so you get the Z twice. So this is Z, which makes sense. You subtract one of the overcounting, and then the answer becomes this, which is true. So there are A number of people here, number of elements, Z number of people, and B number of people here. So this is the main idea. With two things, you can get that like that. For three sets, A, B, and C, we get this formula that if you have A, B, and C, again, you want to know number of elements in the union. And roughly, you want, say, this is union, sum of these things. But again, if you throw some numbers, say there are A many people here, X, Y, Z, T, B, and C, you see that A will be overcounting, right? This part will be overcounting because this is A and all these other things, X, Y, and Z. Whereas this is like B, X, T, Z. And this is also overcounting. This is C, Y, T, and Z. So you have quite a bit overcounting. You can see that X is overcounted because it appears twice here and here. To fix this, what can you do? You can take out the intersections. So you can take out A intersection B. You can take out A intersection C. Take out B intersection C. Would this fix it? Let's look at it. So A intersection B is X plus Z. A intersection C is Y plus Z. B intersection C is T plus Z. So it actually X plus X minus X. So you get one X left. So it X minus X, so one X is good. We already had A and B. This appears once. So we have one X, one Y, and one T. So it actually Y cancels Y, T cancels T. It's almost correct, but I need a Z also, right, to be in the union. Do we have Z coming from here? Do we get a Z from this right-hand side or not? That's my question. No? Yes? Okay, let's look at this. Z, 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 3Z, minus Z, minus Z, minus Z, 3Z goes. So no Z left. So what should I do to fix this? So you need to sum this thing. So this sums normal things. subtracts 2 intersections and adds 3 intersections. So it's like alternating plus minus plus minus. This gives us an idea that if I have finite dimension, like n sets, A1, A2, A3, AN, I should have a formula. So this is the principle. This is what's called inclusion-exclusion principle. Let A1, A2, AN be a collection of finite sets. So they're all finite sets with some number of elements. Then the number of elements in the union of them. So we are taking union of all of them, like this one, is equal to any guess how it should look like? If you were the ones who find this formula, you already seen the case 2, case 3. Can you make a guess? It should look like this. Can you write the formula for 4, for example? If you can write it for 4, you probably can write it for... So what do you expect with 4? So you sum these singles. Okay. This will overcount. Should I first take out the pair intersections? Okay. Okay, then. But what about the 3 ones? Intersection of 3 things. Should I add the 3 ones? Like, these are all the 3s. And then separate, take out all intersections. Would this be a correct formula? If you're lucky, it will be. You're checking. Suppose this is the correct formula. Then how should I state my general formula for general I? If this is the correct formula, it gives you an idea. How should be general 1, right? So how should I state my general formula? Look at this. I mean, there's a pattern here. Like in the elementary school, we learn how to guess the next term in a pattern of numbers. So this is a pattern. You see this, you see this. So there must be something that we can write this in more general terms. So what would you say that general term is? Uh-huh.
The difference we
Use.
like the elements does belong to A.
Uh-huh.
first, feet, then C, then the intersections are added later.
So you separate one of the sets and then inductively write the formula. Yeah, there's a little bit sign of it, but
Do you get iteratively in the problem?
yeah, you could try to. But I was thinking that you could guess that first of all, the formula will be given by these kind of lines, where the first line is just the AIs. Second line is AI intersection AJs. Wouldn't it be like nature, looking at these formulas, wouldn't it be nature to say that this will be some of these things? This is kind of thing I'm looking for. Some of the sets minus some of the intersections. There's all of the pairs. And then plus triples. All the triples. Minus all the fours. Whatever they are. All the fours. And then at the end you get all AN. This was the answer I was looking for. With some coefficient in front of it, which is parity, right? So it should be something like -1 to the n, or n plus n minus 1, n minus 1. Because it's like we get plus with 3, with 4 we get minus, so its parity is just the off one. You could say n plus 1 if you want. That's the same thing. Actually, n minus 1. Yeah. Doesn't matter, it's the same thing. So this makes sense? Is it the right way of writing it, generalizing it? In terms of looking at this 3 or 4 formulas, this is what you will expect? If I say this is wrong formula, would you be surprised? Yes? That makes sense, right? But it's not enough to feel that it's the right formula. We also have to verify that this is actually the right formula for some reason. Okay? So we now have a guess. We guess that this is the right formula, right? How can we verify that this guess is right? Like, we don't even know this is right, right? Maybe we can start with this one. Like, why do you think this is correct for me? Why this was a correct formula? Because we sort of canceled out things. We saw that this is the right formula. Can you do something similar here by being a little bit more clever?
Sadece oradaki hepsinin kesişimini terimlemesini yapmakta.
Aha.
Artı ve artı ve artı ve de 4
Hı hı.
tane yazdık oraya. Eksi ikili şeylerde
Hı hı.
6 tane yazdık. Ondan sonra işte en son bir tane kalması lazım ve de baktığımız zaman bu oluyor.
So what you're saying is that if you have something in the intersection, so if you have something in the intersection of everything, then x is counted. First it's counted as 1, 1, 1, 1 in each of these things. Right? So it's counted by 4 times in the first row. And then it's counted here, 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 here. So it means we take out 6. We took too many times out. And then the same element will be counted here, here, here. So you have to add back 4. Which, like here too, z was like 3 times. We took out 3 times. It's like that. And then thus it's counted here too. You have to take it out 1. If you're lucky, this is equal to 1, right? What's this equal to? 8 minus 7 is equal to 1. So that means this formula counts elements in the intersection in the correct way.
Bir intersection için ama değil mi o?
Yeah, this is only for intersection of 4 things. Can we do, you can do the same thing for 3 of them. So this is one verification. You could do it for the 3 of them. So suppose X is in one of the 3 intersections. Say B, C, and D. Then what will happen? How many times it will count in the first row? 3, because it's not in A. So it's going to count here, here, and here. So it's going to be counted 3 times. How about the second row? How many times it will be counted in the second row? 3 again, because it's in B, C, and D. So it's going to be counted here, here, and here. But none of these things. So it's going to count 3 times in the second row. How about the third row? Once, because it's in B, C, and D. So it's only going to be counted here and none of the other ones. And the fourth row 0 times, right? So it won't count. Do we get 1 again? Do we get equals to 1? Yes. So, right, 3 minus 3 plus 1. So if I take B intersects C intersection D, you get 1 again. What will happen if you get the 2 intersections? Similarly, you get 2 minus 1, 0 and 0. You again get 1. Would this tell us the formula is correct?
For this case it is.
Okay, but all the cases will be similar to these cases, right? In some ways, it doesn't matter which A, B, C, D, you can rotate it. You can always say, if I get 1 here with B, C, and D, I will get 1 with A, B, and C as well, because there's no difference between A and B and C and D. This is a symmetric argument. So this actually covers all the triples, not just this one, right? Yes, no? Okay. So if I say this formula is correct now, would you believe me, or you still need to do some more work? Huh? Yes, no? You believe me, okay. Actually, they say that in mathematics, the worst thing is to believe in something. You shouldn't believe it, right? You should know. Do we know this is correct or not? Let's see if we can prove it. I mean, this is why you're losing. You need to use logic and think about it. Okay, so I will write a proof for this. So the proof will say just that if I count an element in the union using right-hand side, I always get 1. Okay? So we will show that for every element on the union, this means element 2 in the union, the right-hand side counts x as 1. So it will be counting it as 1. That means if every element is counted as 1 on this right-hand side, that means it will be counted as set. It's exactly the same argument with 4 and 3. For everything here, we'll be seeing what does this right-hand side counted as. And if it is 1, then we're done. So we have x here. X in a union of n things, right? You have this n things. A1, A2, A3, and so on. If x is in the union, x is in some of these sets, but it's not necessarily in all of them, right? It could be possible that it's only in A1. It could be possible that it's in the intersection of 2 of them. It could be possible that it's intersection of 3 of them. So this is one of these cases. Doesn't matter which one. But it will be in the intersection of k things and not in the k plus 1 things. Suppose x is in, say, A1, A2, AK, but not in other AIs. Okay? So it is in only of these k of them, whatever those k of them is. K could be 1, then it's in only one of them. K could be n, it's in all of them. Okay? Then we see, so we can see how many times it's going to be counted. Okay? We see that x is counted on the right-hand side. So we look at this right-hand side. How many times it will be counted here? Okay? So let's start with the first row. How many times x is counted in the first row? K times. Because it's in exactly in k of them and in not other ones. So it will be counted k times. Right? Minus. How many times is counted in the second row? How many intersections you can find for x? K choose 2. Because from these k things, AI1, AIK, you can find these pairs, k choose 2 different ways. So it's counted k choose 2 different ways here. How about the third row? How many different ways I can find x in here? K choose 3. You can find all three combinations of these. Okay, so you have k choose 3 here. How about here? K choose 4. So minus k choose 4. Plus and so on. You get the idea that at the end it will be k choose k with some sign which comes from wherever we are. So in the third one it's plus, so it's always k minus 1. So it's k minus 1. So this is how many times it's counted on the exclusion-inclusion long fight. What do we need? We need this to be 1. So the big question is this equal to 1? Yes or no? It's actually 2. Why it is 1 or why is it 2? Any ideas? Come on, guys. You should. So I want this to be 1, right? So the question here is this one. Is same as this question. So take 1 on the right hand side. Take everything to the right hand side. So the same question I can ask if this is 0. Yeah. This is k, but it's k choose 1. So this is k choose 0. So this is exactly plus minus of the k choose i's, which means it is this sum, which we've seen that is equal to 0. I mean, it's 0 here. By the binomial theorem that we studied before, so you can write this binomial theorem. And if you put plus here, minus here, this is what you get. You can see it, right? It's plus 1, minus 1. It's exactly the formula. It goes by binomial theorem. Okay. Do we have any hesitation now? Because I did it for an arbitrary k. K could be 1, k could be 2, k could be 3, 4. So here we were doing case by case. But by choosing some arbitrary k, we actually allowed all the cases. We solved everything in once. And we solved it using something very universal, binomial theorem. Okay? Any questions? There. Okay. Let's solve a question using this. This is a very priceless formula. I mean, many things will come out of it in a very nice way. So, one of these formulas, one of these usages is this.
Can we write this equality in a single line equation?
Yes or no? I mean, you can write it, but you need to use sigma notation. So you could say it's union I1 to n ai union is equal to sum ai's 1 to k plus ij's ai intersection aj's. Then you use minus plus like this. So you can use the sigma notation. The generic term will look like this. And then you finish with the last one. So this will be. So, I mean, but I like this way too, because you know this is the singles, intersections, triples, and so on. So you can also write it this way. Let me write a question to solve. Find the number of positive integers less than or equal to 1,000 that are divisible by 3, 5, or 7. Any idea how to solve this, or any idea how to apply this? I mean, it's almost obvious that you need to apply this, but maybe sometimes you come up with different arguments. So, how do you solve this? Because it says or, this is a little bit more different, right? All the ones is divisible by 3. You sort of can find, you can find the ones divisible by 5, but you're supposed to find or, like union of these sets.
Find
Uh-huh.
the divisibility of integers
Uh-huh.
separately, then find the two combinations, and
Uh-huh.
find the three.
So let's call A, B, and C, and say A is the ones divisible by 3. And this is divisible by 5, and this is the divisible by 7. And the question asks or means you're supposed to find the union, number of elements in the union. So what's the number of elements in a union? We just saw that it is by this formula, or by the 3 case of it, the sum of each one minus the intersections plus triples. And this is all of it. There's nothing else in this case. So how do you find number of elements in A? 1000 divided by 3. 1000 doesn't divide by 3, so huh? It's the there's a bracket notation. Maybe some of you know it. So number of elements in the set A. This is the number of integers divisible by less than or equal to 1000 divisible by 3. So this is roughly this, right? But this is not the integer, so we need to say it is the, so this is 333 point something something. But if you want the exact number, it should be 333, right? Because you don't have 1000, you don't need 1000. So how do you get 333 from this? You just say the biggest integer less than this. So for an integer x, this is the largest integer less than or equal to x. This is the notation. So we can do the same with b. In that case, actually just 200. You don't even need the sign. With the 7, you can use this notation. So roughly, it's actually equal to this. We can actually write the numbers. This is 333. How do I find the intersections? What is the intersection of two things? What will be the all the integers divisible by 3 and 5 at the same time.
21
Sonuç
olmuş.
mantıklı.
21 olmuş.
They're the ones divisible by 15. Because 3 and 5 is primes. So if something is divisible by 3 and 5 at the same time, it should be divisible by 15. So you get 1000 over 15. What is this number? Anyone check? 6? 60?
Açalım.
66. Okay. How about this one? So C is A intersection C is the ones divisible by 21. What is this number? 47. How about B intersection C? $35, 20. And what is the intersection of all of it? $105, 9. So you just add these numbers, subtract these, add the none. Okay. So the answer is 333 plus 200 plus 142 minus 66 plus 47 plus 28 minus 9. Whatever that is. Okay, so this finishes the inclusion exclusion. In the next hour, I want to do stirring numbers, which is important for solving combinatorial problems. And we'll be developing the stirring number using this. Okay? Let's take a break and we'll continue.